Hi folks. Up until now in Algebra 2, you've done a lot of graphing. In fact, you just had a test that was over graphing. And so graphing could mean on a coordinate grid, like an X and a Y axis, but it could also mean on a number line. A few days ago, we moved away from graphing and we started solving absolute value equations. So we started doing more algebraic stuff. Right now, what we're going to do is move into 1-7. It's solving, so we're still kind of in that algebraic component. So we're solving compound inequalities. Now, in addition to solving, you're also going to be combining some of the things that you learned from graphing. The compound inequalities, what they look like, is if you have something like, let's say you have a number line, and on this number line you have like a -3 that's a close point, and maybe you have a, I don't know, a 2 that's a closed point, and you have all of this stuff shaded in between, all of this, and that's your solution set, and you're trying to figure out how to write this. Well, the left boundary is -3. The right boundary is 2. Let's say my solutions are all of my x values, and I notice that they're both closed points, so I would have less than or equal to signs. So today what we're going to talk about is a compound inequality, meaning a kind of answer like this that has two inequalities built in together. They are compounded. We've got multiple things that we can read out of this inequality because it's a compound inequality. It's got an inequality over here and an inequality over here. So, let me find my text tool. The essential question today is, what is the difference between and or inequalities? And how are their graphs different? Let's see if I can spell it right. How are their graphs different? So what's the difference between using the word and using the word or for inequalities? And how does it make the graph look different? Well, let's talk about candy. Candy is relatable to everybody, so we're going to talk about candy today. Let's say that I like candy that is both chocolate and peanut butter. So if I like candy that is both chocolate and peanut butter, you would say, you must really like what? Well, I must really like Reese's, because Reese's is both chocolate and peanut butter. So it satisfies both. So and inequalities satisfy both inequalities that are there. Now, switching away from our candy thinking and back to our inequalities and graphs, on a graph, if I'm graphing an and inequality, the solutions, remember the solution set is in the shaded area? Well, the solutions, since there are going to be two inequalities here, the solutions are going to be in the double shaded area, sometimes called the overlapping area. Overlapping shaded area. There we go. So if I have an overlapping shaded area that's representing my solution set to a pair of and inequalities, that means that there's a possibility that my two sets of shading doesn't overlap at all. And if my solutions are in the overlapping shaded area, but nothing overlaps, well, that means that there's the possibility that there is no solution. That is a possibility today for and inequalities. Now, let's go back to our candy thinking. I'm really liking this candy thinking. And let's say that my favorite candies have chocolate or peanut butter, either chocolate or peanut butter. So, So you might say, oh, well, okay, you must like Reese's, probably a lot, but you probably also like Kit Kat because it has chocolate, or Chico Sticks because it has peanut butter. So, or inequalities satisfy one inequality or the other. one inequality or the other. Either one. So switching back from our candy thinking to our graph thinking, on a graph, solutions to or inequalities, where it satisfies one inequality or the other, they're in any shaded area. So anywhere that's shaded, well, that's a possible solution. That means that I could be shading everything to the left of a number and everything to the right of the number, so the whole number line might be shaded, and I have the possibility of infinitely many solutions, meaning everything is a solution. So, I know it's hard to visualize. It's easier when we talk about candy. It's more enjoyable when we talk about candy, but now let's kind of go to what it looks like mathematically. So let's see some AND examples. Now, in example 1, let me move this up a little bit. There we go. In example 1, you'll notice that you see two inequalities. You see a less than sign here, less than or equal to, I'm sorry, and you see a less than or equal to sign here. That is what you call a compound inequality. Sorry, that's not very center, but it's a compound inequality, and it always indicates that you have an AND situation going on. Your x values are going to be satisfying two different things, something and something else. So the way you solve this, and it seems really complicated because it has two inequality signs here, but the way you solve it is the same way you would solve any other equation or inequality. What you do to one side, you do to the other. So if I'm trying to isolate x here, I would want to move the -7. Well, if I want to undo -7, I would do the inverse operation, which is +7. What I do to the inside, I must do to the outsides as well. So notice how I'm doing it 3 times because there are 3 sections of this inequality. It's not just left side, right side. It's left side, right side, and the middle. So -7 plus 7 is 0. My inequality sign is still less than or equal to. I have 3/4 x less than or equal to, and then -4 plus 7 is 3. So I'm almost there. I still want to try to get x by itself. What I have here, 3/4 times x, is kind of like 3 times x and then divided by 4. I don't want this fraction here anymore. So I'm going to multiply the whole thing, all 3 pieces, by 4. Because that way, I'll get the 4 and this 4 under here to cancel out. 4 times 0 is still 0. In the middle, I still have 3x because I canceled out the divided by 4. And 4 times 3 is 12. So I multiplied all 3 sides by 4. This is kind of tricky, so you might want to pause the video, rewind, go back and watch it again, because this is probably the first time you're seeing something like this. So go try and watch it again. Now that I want x by itself and it's just being tied to the 3 with multiplication, I can divide by 3 to get x by itself, to isolate it. But what I do to one side, I have to do to all sides. So 0 divided by 3 is 0, less than or equal to 1x, less than or equal to 4. Now, this is a compound inequality. However, there are 2 parts that I need to consider. The first part is right here. So that part is that x must be less than or equal to 4. And x must also be something else. X also has a relationship with 0. I notice that 0 is less than or equal to x. However, I'd like x to be first whenever I'm writing my answer. So if I lead with x, that means that my symbol connecting it to the 0 needs to be open towards the x. So if it's open towards the x, that means that it needs to face this way, so that it's open towards the x. Do you see how I'm still keeping the symbol open towards the x? Open towards the x. So these are my two situations that my solutions must satisfy. So if I'm going to graph them, I'd graph both my numbers, 0 and 4. 0, 4. Make sure they're in the right order. Don't put 4 on the left, because on a number line, 4 doesn't go on the left of 0. And I'm going to graph these up top. I'm going to graph them in yellow because it's not my real answer. I'm just kind of trying to see where the overlapping shaded area is occurring. So if x is less than or equal to 4, less than or equal to means a solid closed point. And if the x's are less than or equal to 4, that means that they're to the left. For my relationship with 0, the x values are greater than or equal to 0. So greater than or equal to implies a closed point. The greater than part implies shading to the right. And the overlapping section is this right here. You see that? That's the overlapping section, where those are both being shaded. So I've got a closed point here and kind of a closed point here. Remember, all lines are made up of a whole bunch of closed points. So that means there's a closed point at 0. Closed point, closed point, closed point. And then the overlapping shaded area is in the middle. So that's my solution set to my compound inequality, where x is less than or equal to 4 and x is greater than or equal to 0. So I know that was a lot. You can pause the video, you can try and look at it again, but I'm going to move to example 2. Example 2. Also a compound inequality because I see two inequalities. I notice that the inside has a negative, it's really like a -1 times this. So to undo the multiplication times -1, I need to divide by -1. What I do to one part, I do to all parts. So now this negative is gone. I have x minus 1 in the middle. -4 divided by -1 is 4. 4 divided by -1 is -4. And remember that whenever you're dividing or multiplying by a negative with inequalities, what do you do to the inequality sign? In Algebra 1, you learned that you must flip the inequality sign. It would not make sense to say that 4 is less than -4, so you've got to switch the inequality sign. Now the last step to isolating x is to get rid of that -1. So I'm going to do the inverse operation to add 1. What I do to one part, I do to all parts. So I still have x in the middle. 4 plus 1 is 5. -4 plus 1 is -3. And now I'm ready to write my solution, my answer. So one of my answers comes from here. My x is greater than -3. Since it's a compound inequality, I'm going to use and the other one comes from here. Remember that you want to write the x first, the 5 on the other side, and I want my inequality symbol to open and point to the same thing. So here it's opening towards the 5, and it's pointing to the x. So it needs to open towards the 5 and point to the x with the or equal to underneath. So if I am graphing my solution set, I need points at -3 and 5. I'm going to graph above so that I don't put my final answer on my graph. I want to see where my overlapping shaded area is. So first, x values must be greater than -3. Greater than means an open point, and greater than also means shaded to the right. Here, x is less than or equal to 5. Less than or equal to implies a closed point, and the less than values are to the left of 5. So my overlapping shaded area is happening here. Notice, though, that there is no point at -3, no value, I'm sorry, at -3 because this is an open point. It's like the value was removed out of it. So I don't want to box this in because this is not going to be a closed point. This is open. So this is my overlapping shaded area. I have an open point here because there's no value on both of them. I have shading in the middle. And then I have a closed point here and a closed point here because this line is made up of a bunch of closed points. So that is my solution set. So what I'd like for you to do is pause your video, think about it for a second, try example 3. So pause your video and try example 3. And then when you're ready, turn your video back on and see if you've got the answer right. So look at the work. Remember that if you move this 9 by subtracting 9, a negative x is left over, and in order to get it to be just x, you've got to change all the signs and flip the inequality. So that might be a mistake that happened. Make sure you're careful with that. Now, whenever I graphed these, I noticed that it's an and inequality. Even though it wasn't compound, it's still and there's no overlapping shaded area, which means that there is no solution that satisfies both of these conditions. There's no x value that's both less than -3 and greater than 8 because there's no overlapping area. So I would say that this is no solution. Now, I'm going to move to some OR examples. We're going to do the same thing. We're going to do 2 together. And then we're going to do one where you work on your own. So, in example 4, I have 2 separate inequalities. They're also connected with the word OR, which means that these are OR inequalities. So I'm going to take each one separately and I'm going to solve for x by doing inverse operations. So if I want x by itself, I need to subtract 2 from both sides. I have 3x is less than 11 minus 2, which is 9. And to get rid of this times 3, I divide by 3. I have x is less than 3. Here, I want to move the constant. Subtract 3 from both sides. I have negative 4x is greater than or equal to negative 21 minus 3, which is negative 24. Negative 21 minus 3 more is negative 24. You divide by negative 4, and you get an x on the left side. You divided by a negative, so you must switch the inequality sign, and negative 24 divided by negative 4 is a positive 6. So your answers here are that x must be, less than 3, or x must be less than or equal to 6. So either of these conditions, if they're satisfied, then your answer, or your number is part of the solution set. So I'm going to go ahead and graph my 2 values of 3 and 6. On top, I'm going to do my graphing of each individual inequality so I can see where my shading should be. Remember, for OR inequalities, it's okay to shade anywhere there's shading. So if x is less than 3, that means I use an open point. The less than values are to the left. If x is less than or equal to 6, that means I use a closed point. The less than values are to the left. And I notice that this part right here is overlapping. And that really is great. I mean, if it were an and inequality, I would just shade this section. But I want to shade everywhere that it's being shaded. So the farthest right that's being shaded is this over here. And it's shaded all the way to the left, and then it picks up this other inequality, but it's still all the way shaded to the left. So my answer is just all the x values that are less than or equal to 6, because everything in here is also in here. For example, if I pick a number like 0, That's less than 3, but 0 is also going to be less than or equal to 6. So any number that's in here is also in here. So let's try example 5. Example 5 is another OR inequality. So I have two separate inequalities joined by the word OR. I'm isolating the variable x, so I move the constant with an inverse operation. What I do to one side, I do to the other side of the inequality. X is less than -3. For the second inequality, I want to isolate x by moving the constant with inverse operations. I still have a negative x is less than 1 minus 7, which is -6. And I don't want negative x, I want regular old x, positive x. So if I change the signs, I also have to change the inequality sign. So my solutions are anywhere that x is less than -3, or anywhere that x is greater than 6. So I'm going to figure out what that looks like. I'm going to graph my -3 and my 6. And if x is less than -3, less than means an open point. Less than is all the values to the left. If x is greater than 6, that's another open point. But the greater than values are to the right of 6. Remember that an OR inequality satisfies either inequality. So that means that my solution set that satisfies either one, There we go. So my solution set that satisfies either one is this and also this. So anywhere that you see shading in yellow, that's where you shade for your solution. So finally, we have example 6. I want you to pause the video and see how far you can get. See if you can graph, and then turn the video back on to check your answer when you're ready. So there weren't any super tricky things in example 6. We have basic inverse operations going on to solve and isolate x in each inequality. When you graph, you have all the x values from 4 and to the left that are less than, and we're holding a spot for 5. It's an open point, but we still have the less than symbol, so shading to the left. That means that anywhere there's shading, I get to shade my answer. Now 5 is an open point, and it's shaded here. And then both are shaded here, so I get to continue my shading in that direction. So technically in example 6, the solution is all of the x values that are less than 5. Because anything I pick here will automatically be a true value here. Anything that's over here will automatically be in this area over here.